Yes, thank you very much, and thank you for the opportunity to talk at this conference. I'm going to talk about research I'm doing together with Hans Munterkos, my supervisor, as a part of the Codisma project. And first, we start with some basic differential geometry. I'm very fortunate, once again, that for the second time that I hold this, well, it is the second time I hold this specific presentation, and also the previous time I was after Dominique Manchon, and he does a very good job at laying out the foundational definitions that we need, but we will repeat them quickly. So we will consider a smooth manifold, and we will look at all the smooth vector fields on the manifold. And we will, if we have an affine connection, that is a map that takes in two vector fields and gives out a new vector field. And it is also R bilinear. So what we're going to do is just to, I'm walking ahead of myself. First here, we just look at all the definitions, right? Is there like a pointer thing here? There, look at this. So this is just the definition of the connection. And these two definitions, the one of curvature and of torsion, they will become important later. But what I really want to introduce is this thing that we call the connection algebra, which is similar to what Dominique has been talking about. And we would just consider the connection here as a product on the vector space here. And that is going to give us some algebra here that we will call the connection algebra. And since, like Dominique, we're going to algebra, so we're going to tilt triangle down like this for simple notation. And I want to just look quickly at this here. If you take the curvature of x, y, z and minus the connection of the torsion of x and y acting on z, you can write it out, and it's almost immediately going to give you this equation. And this and this is going to be a very important thing. So we're going to make an abstract algebraic definition of this, which we call the triple bracket here. And it's just going to write out exactly this relation. So when you see the triple bracket, throughout this talk, you can always, you can think of it as you could loosen it up, and it's going to look like this. And for those that are not familiar with this relation, I just want to emphasize that this first part, the two terms here, will be 0 if it's an associative product. The second two terms here will also reduce to 0 if it's associative. So this is all 0 if it's associative. Moreover, look that this first two terms is just equal to the second two terms with the sign switched and the two first arguments switched. So it's skew symmetric in the first two indices or arguments, and here is our framework. Okay, so in 1954, Numitsu classified the manifolds that are associated with invariant connections. And those are that if you have 0 curvature and 0 torsion, you are on the Euclidean space. If you have a connection that has 0 curvature, but your torsion is parallel, that is associated with a Lie group. If you have a parallel curvature but 0 torsion, you're on a symmetric space, or I guess it could be a locally symmetric space. It should probably be locally put in here. And then the last one is a reductive homogeneous space. And previously, this connection algebra have been studied in the case of Euclidean space, and you get a pre-Lie algebra. And in the Lie group case, you get what is called a post-Lie algebra. And then in the case that I'm interested in, it's going to be here over the symmetric space, and we've called this algebraic structure a Lie admissible triple algebra. So a little bit of motivation for why we're looking at this. So for people that are interested in the numerical approximations of differential equations, one tool to study those are B-series. And that's when you're looking at equations that are coming from Euclidean space. And the underlying algebraic structure of B-series is pre-Lie algebras. And these have been generalized to Lie groups. And in the case of Lie groups, you have Lie-Butcher series, and the underlying algebraic structure are post-Lie algebra. And then I found this quote that kind of anticipates the results and research that I'm going to put forth today by McLachlan and Moudin and Munterkos and Badiev. So, yeah, it's just trying to motivate for why this is interesting. Yeah. Oh, did I? Yeah. So just to introduce some notation here, I'm going to talk about, okay, so if you have a set C, then you can just think of it as, yeah, the free magma is going to be if you just have a product on your set, a bilinear operator, or just not bilinear, just operator that takes in two arguments. And you just freely generates new elements from your set C. It's called the free magma. And I will define this alg C as the free algebra that is spanned by the free magma over some field, usually just R. So this is just the free algebra, and it could be represented by the span of all planar rooted trees that are colored by the elements from C. So I would often refer to C as just the colors, the set of colors. And the product is then represented as left grafting. So if the set C only contains a single color, like down here, the first few elements you get would be these ones. So one of that is just a single element, and the product of the two, and then there's two of order three, and then there's further one. Notice that these two are different in this case. And then we have the what's called a Preely algebra. So a Preely algebra is an algebra that satisfies this relation. So exactly this that I have also defined to be a triple bracket. If this is 0, you're in a Preely algebra. And then I just want to make a remark that earlier I argued that if you take the curvature and the torsion against each other in this way, you write out exactly this relation. So if both the curvature and the torsion is 0, the connection algebra is a Preely algebra. And then the free Preely algebra is, okay, so if you let J be the ideal in the free algebra that is generated by the triple bracket, that is exactly the relation that is supposed to be 0 in the Preely case. Then you can say that the free Preely algebra is isomorphic to the free algebra quotient out by this ideal J. And this has been described earlier. It's from Chapeton and Livernet, or also done by Juma Dildayev and Lefvol. They have both arrived at the free Preely algebra can be represented as the span of all non-planar trees that are colored by the set C with a grafting product. Now, what's really happening here, remember that the free algebra was just all the planar trees colored by C with left grafting. So what happens when you quotient out by this ideal J is really just, if you look at this example with just a single color, you get, it looks like the same until here. And you see that now these two elements are equal. So what happens is that in the free Preely algebra, the order of the branches on your trees don't matter anymore. That's exactly what happens when you quotient out by this ideal J. Okay, and now we come to the algebra that I'm interested in, which is the Lie admissible triple algebra. And that is defined as an algebra that satisfies these two relations. So the first one you can see here, it looks similar to the Jacobi identity. It's just saying that the cyclic sum over the arguments here should be 0 in this way. And the second one, it says that if you multiply something with a triangle product into this triple bracket, it acts like it jumps in as a derivative. So any algebra satisfying these two relations is called Lie admissible triple algebra, or LAT for short. And just a reminder, this triple bracket is not a unique operator by itself. You can always just factor it out and write it like this. The name comes from the fact that the first equation here is exactly the necessary condition for the commutator of the triangle product to define a Lie algebra. That's why it's called, this is also than just a Lie admissible algebra. And in addition, we have this second relation here. It implies that if we take the triple bracket off, and the last argument is again a triple bracket, it would, these two could factor in like this. So the triple bracket acts as a derivative on itself. And that means that this, the algebra with the triple bracket defines a Lie triple system. I want to talk quickly about symmetric spaces. This is the definition of a symmetric space as given in the book by Ottmar Loos. And it is a manifold with a smooth map such that, and I just write a dot for the smooth map, x on x is equal to x, x on and then xy should be equal to y, and so on. It should satisfy this relation and this last one. And a few examples here is just a Lie group would always define a symmetric space if you define this smooth map in this way, using the group product. And the unit sphere defines a symmetric space if you define this product in this way. And Grassmann manifolds you could also give them the structure of a symmetric space by defining this product to be just reflections of linear subspaces over each other. Yes, and then from this article by Nomitsu that I referred to in the beginning, it's shown that any smooth manifold, for any smooth manifold, these two are equivalent. That if you have a symmetric space, then you also have a connection, affine connection that satisfies zero torsion and parallel curvature. Okay, so the case I want to make is just that, okay, so the thing I have defined as a Lie admissible triple algebra is really just the algebraic structure that came forth when we studied the connection algebra of a symmetric space. So now, so I'm just going to show you how that happens. If you have zero torsion, then remember that this triple bracket, this whole relation came as the curvature minus some term involving the torsion. So if the torsion is 0, then this triple bracket is now, it could be thought of as the curvature of some manifold. And if using the first Bianchi identity, almost immediately, you would then arrive at this equation, which was the first of the two defining properties of a Lie admissible triple algebra. And since the curvature is parallel, again, just translating this to what it actually means, and then noting that the curvature could be written as a triple bracket, you just get this equation, which is exactly the second defining property of a Lie admissible triple algebra. So indeed, this algebraic structure is associated with symmetric spaces, as it is the connection algebra of a symmetric space. And now I want to talk a little bit about trees. And I'm just giving you a minimum to be able to state the main result. But this is just some notation on trees, I guess. But if you have, so T of C here is just the set of all planar rooted trees that are colored by the set C. And if you have elements in, okay, so x1 to xn are now rooted trees, planar rooted trees, then I can take all these planar rooted trees and just graph them onto a common root and get a new planar rooted trees. And here's an example. I have three trees, and I graph them onto a root, and I just have in the same order they are here, and you get this. But I want to have something slightly more general, and it's so it's one way of representing non-planar trees would be to, in a way, So a section of the space of all planar trees, the non-planar trees can make a section among the planar trees. And one way of doing this, instead of defining an order and choosing a representative for each class of planar trees that is associated with the same non-planar trees, we can symmetrize it. And then what we would do here is just, if you see this S, instead of just grafting it on in the order they are, we graft them on in all possible permutations, and then we divide by the number of permutations. So this main result I want to present here is that this space, the Lie admissible triple algebra, if you look at the free Lie admissible triple algebra that over a set C, then you can generate a basis in this way. That is, all the elements of C is also inside of your basis. If you have 3 elements in your basis and you put them into the triple bracket, and this triple bracket is whole, I'm not going to talk a lot about it, but it's similar to how you have whole elements in the free algebra, free Lie algebra, I mean. So there's just slightly more, some more conditions you need to meet, but it's easy to check. Then this triple bracket of elements are also in your basis. And if you have n elements in your basis and you graft them onto a common root in the symmetrized sense, it's also inside of your basis. And this basis is actually a basis for the freely admissible triple algebra. So a quick outline of the proof here. So I want to refer back to Lefbvre, since that was a key article to starting this process of describing this space. What Lefbvre really proved is that if you have this, that this is a short exact sequence. That is, you have the ideal J inside of the free algebra, and then that's exactly the kernel of the projection down to the free pre-Lie algebra. And another way of stating this is to say that if you have 2 elements in the free algebra that maps down to the same element in the pre-Lie algebra, then the difference between them is contained in the ideal that is spanned by the triple bracket. And that's the ideal, that's the concept that we're sort of generalizing when we're doing this proof. So now I want to define an ideal I that is defined by these 2 relations. That is exactly the two properties of the admissible triple algebras. And firstly, we note that the freely admissible triple algebra is then just the free algebraic structure quotiented out by this ideal I. And the second thing to note is that all these terms involve triple brackets. There's no terms without triple brackets. So this ideal I is contained in the ideal generated by the triple bracket. So I could also split this up and say that our freely admissible triple algebra is going to be the free pre-Lie algebra plus something, not the whole ideal of J, but some of it. Yep. Okay, so what did we do? Well, instead of just having one ideal J, we made a descending chain of ideals, where the first one, J0, is just a full free algebra. The next one, J1, would be equal to what I previously called just J. And then we generate the rest by these rules. So if you have 2 elements in Ji and Jj, then the product of them would be in Ji plus J. And then if you take the triple bracket of 3 elements, it would be the sum of the grade of the elements plus 1, because you have a triple bracket in addition. So what these do is just, it counts out how many triple bracket at minimum you could write an element with. And this lemma is just a generalization of what this corollary. It says that if you take the difference between 2 elements that project onto the same pre-Lie element, it's the same as saying that if you have 2 elements that are just similar up to reordering the branches, the difference of them could be captured in the triple bracket. what I'm saying now is instead of if you have if you have an element and then you reorder the branches of that element and you take the difference, what you're really doing is that you're jumping down to the next level here. So it's the same idea as in left wall, it's just generalized. And I'm going to be very quick, but what we did then is just, okay, so we try to capture this grading, fix it so that you always have control on how many triple brackets your elements contain. So doing that is just taking this ideal that we define and take the quotient of them and generate these spaces nk. And then each nk consists now only of elements that have exactly k triple brackets always. So we fix the number of triple brackets, and then just a quick example of how this is done. These two elements here are written out as you would normally write out planar trees. And the difference between them is exactly this triple bracket, and it's the simplest example, but it's also the most informative, I think. What we do is that instead of writing it like this, we will write this element in this way and this element in this way. Thus, we always see exactly where there are triple brackets and how to deal with it. And then the proof is just quickly showing that our free algebra is contained in the span of the bases. That was the easiest part. And the more difficult part where we needed this grading structure was just showing that, making a projection that checks through, and we see that our basis actually is exactly the admissible triple algebra that we were looking for. And I think I'm going to end with that. Thank you for your attention.